Okay, so today I'm going to speak about something which is called as adversarial learning. Now, what you need to keep in mind is that this is not, so adversarial learning is not only generative adversarial networks, but there are also a lot of things beyond that as well. So, I hope my screen is visible to all of you. I mean, the slides are showing up properly, right?
The Jamboard is visible.
Okay. Now, this typically, so the reason why I wrote down that I will be starting with generative adversarial networks or some sort of generative models is because it makes it easier to introduce this concept of what adversarial learning essentially is. So a generative network is something like this that say I have some data picked out from a random distribution. This goes into some sort of a model, a DNN, which is known as a generator, and out comes a image. So this may be called as, say, called as Y, called as X, and this data which goes over here may be called as Z. Now, typically, how it's characterized is that dimension of Z is less than equal to dimension of this X. This is typically a practice. It does not necessarily uh, always imply that the dimension of Z has to be lesser. But if it's not the case, then there is no great advantage which you would see with a generative model. And you could have basically stored all the exact values of X and instead of trying to generate it from Z. That is one of those points. It is very, very impactful and very necessary for uh, your of just hold on a minute.
Hello, sir.
Now wait, just hold on. There is some very bad banging noise going on just above my head. Just resume it. Just a minute. Okay, so the first type of network which we are looking at is an adversarial autoencoder. So essentially what happens over here is something like this, that if you recall from an autoencoder, you have a network which is called as an encoder. You have another network which is called as a decoder. So the whole purpose was something like this, that you give an input X to this encoder. There will be some sort of a lower dimensional representation getting generated over here. And then you get an output over here, which is supposed to be a prediction of X. And the way you train these is, so your loss function is written down as an L2 naught between X and X predicted. So the objective is minimize this J. Now, typically, the size of Z is less than the size of X. This is what is typically seen over here. So now comes the next part. So these autoencoders, if you look over here, then what would happen is something like this. So you have this
Hello,
encoder
sir.
over here. Yeah,
Sir, some of us are facing the issue that you are not visible to many of us.
I am not visible to many of you.
Yeah.
Interesting. Wait,
And neither the screen.
neither is the screen. The only thing which I can do is I can do a spotlight. This is one thing. The other thing what I can do is I can reshare the screen. The only problem is I cannot give you the link of the Jamboard now, because if everybody clicks on that and joins, I think it does not allow more than 12 people to simultaneously access it. So if more people get onto that one, then suddenly if I get locked out, then I am lost.
So almost 50 people are not able to join this.
Now is it visible?
Sir, those people are not
What?
in this. Like around 50 people are not able to join this meeting. So they are like in another meeting, and this one is not.
Why are they not in this meeting?
Yes, sir. Sir, for me also, this meeting was not able to, was not showing in the Teams, sir.
Yes, sir. Like it was another meeting. When I joined it, there was only 50%, and you are not present in the meeting, sir.
I had to join
Okay,
it.
so that
First, sir.
just hold on. So then somebody started a wrong meeting because this is what it shows on my calendar.
So this meeting is not showing in this Teams app.
Yes, sir. Yes, sir.
This meeting is not shown in the same. It shows only one meeting, and we joined that, and you are not in that meeting.
Yes, sir. Right now, this
the
meeting is not
link
in.
Wait, hold on. I can very clearly see that this meeting is given to the complete group of classroom. Okay, so this should be there. Now the point is, if you had joined this Teams of classroom after the meeting was created, then you did not get this message and it did not auto sync up. In that case, what you will have to do is you will have to go to the MS Teams on our class, then go to the start of the chat. At the under general, at the start of the chat, you will be able to see the link to the 3 meetings for each of these days. Now for each of them, click and add to your calendar. Then it will ask you add series or add occurrence. So you have to add the add series. Then it will be there in your calendar. I thought this is that's why I never even told you. So that is something you have to do on your side, and then everything will come up, because this is created within the calendar embedded thing itself and sent out to the group chat. Maybe if you are not part of that group, then it did not come up.
Actually, sir, I think, sir, there is a technical issue in the Teams side, because it is very general from about 100 people, and now it is showing, sir. So I think that is from Teams side, sir.
If there is a technical issue on Teams, you have to write to Microsoft. If you tell me in the class, I am also a user like you. I'm just using it to teach because institute gave me this one to teach. Now, if you
No,
come
sir,
and tell I did not subscribe to it, I did not develop it, I did not do anything. So
no, sir,
technically, what can I do to solve it?
yes, sir, just like sir, I was saying, sir, that that is the, I think, the issue, sir. That is.
It is not the issue. The issue is that you had not pulled it to sync with your system. There was a sync problem. And most people have not done it. So that's why the sync problem persists. Okay, getting back to class. So typically, if this autoencoder, you will have this encoder, which is a neural network. You get this input image X, which comes down over here. And then from here, you get a latent representation, which is Z. Now the point is that since dimension of Z is less than dimension of X, so in that case, you will be able to see that a lot of this information essentially gets compressed over here. Okay, it's essentially reduced. Now the point is that if this is the case, then we'll have to look into the fact that I do the other. So this is my case of compression. Now comes my other part, which is of. So you look into my so idea is something like this. This one is this Z. Now the point
Sir, your voice is
is,
breaking, sir.
I did not hear anything whatever you said.
Sir, your voice is breaking.
Yes, sir. So much lag. Ah. Honestly, these are like beyond my control. I will try to go as slow as possible and do it. If I mean, institute network is failing, it's breaking. I don't know what to do. So if Z is being fed directly to decoder, then it can generate images. So now if I want to actually sort of give you a example, as in a very simple illustration. So my thought over here is something like this, that say I have a image of an apple which is x1. I have an image of a what is it? Of a ball, okay, which is x2. So this is apple, this is ball. Yeah, I mean your x3 can be C for cat as well. There is no issue. So now here, when I take this and I pass it through an encoder, let a Z1. I pass it through the same encoder, I'll get a Z2. Now the point is, if I take some sort of a representation over here and say my Z's are two-dimensional. So this is the first dimension, this is my second dimension. So Z belongs to r to the power of 2 plus 1. So in that case, what you would end up getting is that Z1 may be a point somewhere over here and Z2 may be a point somewhere over here. So now, if I do this thing into my decoder, if I take this value of Z1 and feed it over here, I am supposed to get down technically an image of an apple, but it's a predicted image. Similarly, if I take the same decoder and feed this data point Z2 as an input to it, then also then I'm going to get down the same image, almost the same image of a ball. The question is that, say I take a point in its neighborhood and I feed it to the decoder. What do you think will be the output over here? What should the output look like?
Some combination of Z1 and
Any
X1
thoughts?
and
Should Can you repeat once again?
So some combination of z1 and z2 as a linear combination of 2 points in a plane.
Okay. I mean, a linear combination should have made that one was on the straight line, but okay, somewhat. So this would be, but in general, what you can see is that since this, let me call this point as Z3. Z3 is near Z2, so X3 hat may be like a ball. This is at least some comment which I can give over here. Yes or no? Do you think this is what I can somewhat say?
Yes, sir.
So now, if that is a possibility, what you would end up having is a pretty interesting thing. So now what I can do is, say I have this kind of 2D space. And I am looking at some sort of distributions such that if I draw samples from here, these are all samples of apples. These are all samples of ball. Now, if this is the scenario that somehow we are able to, if we can impose a distribution model on Z, then we can generate images corresponding to randomly drawn samples. So it will be very easy for you to sort of like generate images. So what you need to do is you will have to randomly draw samples from this kind of a distribution model, and from there you will be now able to generate these images as they keep on coming. So what I am doing now is that I have this distribution model, and what I am saying is like this. So I will be able to generate, say, the series of different kind of apples corresponding to every point. So say this apple is corresponding to a Z which comes from here. This one is something which comes from here. This one comes from here. This one comes from here. Okay. So this is a set of images of apples which are randomly generated. This is what you will see. Now, similarly, this can be a set of images of balls which are randomly generated. You take this and then you keep on generating. Now, as a result of which, what you can now see is that this can enable anyone to generate a lot of random samples of any object class for various uses. So if I'm able to generate these kind of data samples, then what do you think can be the kind of uses where they can be applied to?
So, like virtual clinical trials.
Virtual clinical trials. Okay. Then
So creating KVCT images from MVCT.
I did not understand. Tell me once again.
So like MVCT is like mega voltage CT, and like KVCT is
Okay,
kilovoltage.
okay.
So kilovoltage has a better.
I mean, basically whether your CT energy is in keV or MEV, that is what you are changing over here. Your X-ray is a keV X-ray or a MEV X-ray. This is what you are changing.
So that treatment units have mega voltage imaging, like, so they like they treat it for like adaptive radiotherapy. So when the patient is there, they will match the features using a MVCT. So that is like a poor version. So like there are some papers where they have like created a KVCT from that MVCT.
So essentially, you can do an image-to-image translation. We haven't yet come to image-to-image translation. As of now, we are looking at the point where you are able to generate images from some random element. In this particular example, which I took, you just have two numbers because your Z is just a two-element representation tensor. It has only two scalar numbers. So it's a 2x1 matrix which you put down over there. Now, if you put a 2x1 matrix over there, then what is the kind of image which it generates? That's the point. So now tell me that now that you are able to generate so many images, so what can be the uses with this one?
So are these also used in deepfake videos and or like
Yes.
making?
Yeah. Deepfakes are something which do originate from adversarial learning, from any kind of generative model actually. So the term adversarial learning is something which you use to train a network so that it becomes a generator. This is the difference. So GANs and adversarial learning are not the same thing. A generative adversarial network is a network which has been trained adversarially. Now, what more can you do? You can do deep fakes plus. But deep fakes are still, you're trying to morph somebody else's face or somebody else's expression on some other person. What else do you think you can do?
Sir, making the dataset bigger by applying some generative network over an image to create multiple images of similar kind.
So you can essentially do a dataset augmentation.
Yes, sir.
However, like a bit later when we go, data set and solve your problem. Because you could have rather included all of these things in the same network when you wanted to do the classification and trained it in a better way. So that's something which comes down in tomorrow's class itself. What more? What more? See, have you heard this term called as CGI, computer generated imagery?
Yes, sir.
Do you know what computer generated imagery is? Do you know what it is?
No, sir.
No. Okay. Do you know animation? Have you seen the movie Avatar?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So yes, yeah. So over there, have you seen those crowds? So one is like you might have seen the faces of these actors and everything. So they were using some sort of face tracking technology in order to do it. Okay. But then have you seen all the other forests? Then they created some other like species of people who are moving the crowd over there and everything. So typically, when we create those kind of replicable structures, say in a computer graphics, you want to create a tree. A tree will be made out of lot of leaves. Now every leaf is supposed to be unique. So the same leaf does not come at multiple places. Just hold on a minute. So now the point is that each leaf will have some sort of similarity to each other, but they will not be the same leaf over there. So now, if each leaf is somewhat similar to each other, but it's not the same leaf, then there would be a need that you have some random perturbations of the shape and size of the leaves which are generated over there. Will it be so?
Yes, sir.
Yes.
So now you can actually use this kind of an adversarial autoencoder like mechanism in order to generate that. So what you will have to do is you will be able to get down a lot of leaves coming over there where their more or less structural similarity is similar to each other. They appear as if, okay, they are the leaves of the same kind of species of plant or from the same plant, but then the no two leaves are going to look very similar to each other. So that's something which can be achieved by these kind of methods of generative adversarial network. Okay. So now from here, so starting from here, essentially, what we need to understand is how do you train? How do you train the adversarial autoencoder? This is the next part which we need to understand. So now let's look into this one. So this is typically what an adversarial autoencoder looks like. Now how it works is something like this, that you give an actual input of a particular image. So this can be, say, set of multiple images of apples. This can be set of multiple images of balls or something. But as of now, we'll keep it congruent to a certain class, and that's how we will move. So you give all images, say, of apples, which is an X. It goes through this encoder. You have a latent space over here. Then it goes to the decoder, and out comes down a predicted map over here. So now that it comes out, what I can do is I can find out one particular kind of a loss over here, which is called as J1. So this J1 is X minus X hat and an L2 norm over that one. So typically this kind of a loss is called as a reconstruction loss. And one way of training this is essentially that you backpropagate this loss through these, backpropagate the gradient of these loss through the encoder and the decoder so as to minimize this loss. So your backpropagation is with J1, nabla of J1. Okay. Now that you have backpropagated with this nabla of J1, which is good, the next part which comes from over here. So what I wanted to do is I had a certain objective, and what that objective was, that objective is that the Z should follow a certain parametric distribution PZ. This is what I wanted to follow. Now this parametric distribution is this distribution. So say that this comes from this particular distribution. I can draw some random samples. So Z prime is actually a random sample which is drawn from PZ. Okay. Now what I am doing is I create another neural network over here, which is called as a discriminator. Discriminator discriminator is also a neural network. Okay, so now that this discriminator is a neural network, your job is to see, so the discriminator's job over here is to see whether it can discriminate very appropriately between Z prime and Z. So what this discriminator is doing, so you have another loss, J2 is equal to ability of discriminator to differentiate between Z and Z prime. Okay. So initially when I start this whole training mechanism, all of these Z's, so for every corresponding X, there will be a Z generated. And what you would do for this purpose, you will generate a random Z from here. You feed, when you feed this one through this discriminator, the expectation is that it calls this as fake. When you feed this one through the discriminator, the expectation is that it calls it as real. Okay. Now the point is that initially you don't, this network somehow or anyways, this whole network does not know what is this distribution. So in general, these Z's will be very different from this Z prime over here. And you can pretty much train your discriminator over here, which is also a neural network, in order to minimize the loss J2. Because that is the only loss which you get down in your discriminator, which you can minimize. Now, while you are minimizing this one, there is an interesting thing. So while this J2 gets minimized, I also have an objective, which is that can I actually sort of modify my encoder and decoder in a way such that now it starts generating this Z which very much mimics Z prime. So I want this Z to follow the distribution PZ, but I cannot compare a particular representation, a particular number to a distribution. I know that the number might have come from the distribution, but I cannot compare a number to a distribution itself. So, but I can compare numbers to numbers. So what I'm doing is, while I'm pulling out a random value, I also have this exact value of what is the code sequence corresponding to a particular class, which comes down over here, and that is Z. Now, as I get that, what my objective is that can I force this encoder to behave in a way such that it modifies this Z? So here comes my next part of it, which we call as an adversarial loss. So adversarial loss or JADV, this can be written down as something like 1 minus J2. Now the reason I'm saying that this adversarial loss can be written down as this is because what it would do is, say initially what I have is this Z is very different from this Z prime. So this adversarial loss J2, this J2 over here, that is going to be very low. So if that is very low, then this encoder should know that it has to modify itself because whatever it's generating is not similar to this one. So now my adversarial loss is very high. Now if adversarial loss is represented like this, then I can write down this as nabla of J adversarial, which is my gradient which has to go, and then that for our representation it is going to become minus nabla of J2. Okay, so there is a sign reversal which happens over here. So in case of the discriminator, you update only with nabla of J2. In case of the encoder, you update it with minus nabla of J2. So that is something you can do for actually updating the parameters of your encoder. Now, what comes out is that as this keeps on progressing, so what you are doing is you are going to force
Hello,
this
sir.
head. Yes.
Sir, time is over, sir. I have another class. Sir.
Oh yeah, just move on to the class. I will also end up. So now that this set will start becoming very closer to the Z prime over here. Okay. So let me close till here as of today. Tomorrow I will get into detailed loss function as it progresses with the training. And from there I will get you into the generation principle itself.
Hello,
Okay.
sir.